So I hope my microphone works right away, and thank you very much for coming. Right, I'm very happy to see so many people here. Yeah, sorry for the meta talk not being present, but I hope I can fill in with something that interests you. So as this is really hands-on and live, everything can go wrong, of course, like always when it's a live demo. We tried our best to make it work. But the good thing is that you can always ask questions, and we can go deeper at any point if you like, right? Especially now that we have more time than I initially thought. And you can see that it's for real. Just 2 words about myself. I'm a Zephyr maintainer for the 802.15.4 subsystem, so everything that is below, at driver level, below thread and open thread, meta as well, right? But that's for maybe 2 years now that I'm working in Zephyr intensively. Since almost 1.5 months now, I'm working for Grandcentrix as well. And it's great because they help me to continue my maintenance work at the same time as I'm working for clients. So this is a great combination for myself. So whenever you have any ideas what you want to upstream in Zephyr, tell me, and I'll help you to get it upstream. Okay? Good. So our talk today, there the problems start. Let's see, yeah, but it will work. That's it. So, very simple agenda, of course, right? Because the most important thing is the demo. I'll show you a little bit what you can expect, right? So you get a first impression. I did very nice screencasts, actually, of my measurements, also as a fallback, right? In case anything goes wrong. Unfortunately, the software I'm using here doesn't support GIFs, so it will not be animated, but we hope that the real stuff will be animated, so that doesn't matter. Then I have to introduce you probably a little bit into what we are actually seeing on screen, because this is a real problem that I solved by tracing. And it's a quite complex problem very low inside the controller stack of the Bluetooth Low Energy ISO channels. Who of you knows what ISO channels are? How many people have ever heard of it? Bluetooth audio, BLE audio. I see people nodding here a little bit. So it's bleeding edge technology, and you know Bluetooth audio? Yeah?
Not really.
Okay, I see. So it's bleeding edge technology, and that's why you probably don't know about it, but that's also the reason why we still have bugs in it, right? So it's a thing that was defined in Bluetooth 5.2 specification. We are now at 5.4, and yeah, we are still waiting for the real applications. Maybe hearing aids or something will have Bluetooth Low Energy audio right away. Show you a little bit about that so you can understand what you're actually seeing. And I think it might also be interesting for you to see how such a low-level protocol is working and see it really live, right? Next point, tracing, of course. I'll show you what we can see on the trace later so you understand that. I show you how it looks before and after the bug resolved. And then, of course, you have a lot of time to ask questions and give me feedback if you want. Okay, let's start. So we are using here actually usually non-free tracing tool from Sega. I'm in no way related to them, right? So full disclosure. But we are using their friendly license. So when we are doing stuff for open source, it's explicitly permitted, or educational use, which is actually our case here, is explicitly permitted to use this tool, right, and show it off. But if you want to use it in your organizations for commercial purposes, you will have to license it, right? But that explains why you'll see sometimes non-commercial version, etc. That's fine, okay? What we see below is the PPK2. It's a small tool from Nordic that probably some of you will know. It helps me to usually measure power consumption of devices. In this case, we'll use it as a side channel attack, kind of, right? So we can see here that the tracing results do immediately match the power consumptions. So we can use both channels interchangeably, and that's also something that I'll try to demo live on screen, right? The combination of both is very nice if you're doing debugging of especially radio protocols, because they always have this clear spikes when they are sending things or receiving things, right?
What do we see on top?
Here?
Yeah.
So you see on both, so you see the same thing really, right? And I tried, I'll go much deeper into this in a moment, but you see that packages are sent and received, right? The central, the peripheral, these are the two Bluetooth roles, and these are the intervals of this isochronous. No, but I'm going to go deeper into it for you to really understand it. And you're seeing the same thing here and here. Here you have the view inside, what is happening inside the kernel. You see the different interrupt routines here that are being called. You see the threads, Zephyr threads that are being called, and you see their activity really while this is happening, right? So this is one and the same thing, just two different views on it.
Yeah, it's not really readable from here, so that's why I asked.
Oh, I'm so sorry. Yeah, I see. No, I'm going to read it for everyone, right, in a second. So, yeah, that should actually be something that is animated. So I'll try to do this by just, okay, now you can see it, right? So what you're seeing here is how it should look like. I'll tell you in a moment why it should look like that, but you can see it's very stable, right? Very deterministic. Here packets are being sent of different sizes. You see that the size of the package is increasing live. This is really a live screen capture, right? And you can see how the package is being prepared here, etc. Right? We are talking about one physical packet that we are looking at actually, and that's what you're going to see live after the bug fix. I also linked in the bug. So sorry.
Are you triggering on one task? Or?
Yes, exactly. I'm triggering on a specific real-time counter here, right? So it really looks stable. But that's a challenge, right? You need to find a trigger point that makes it stable so you can see it really. And this is, of course, a GIF loop. So this is going on for hours because actually I just capture two packets and then it goes back. But if you see it for real, you'll see that there's some things happening in between, but still you should recognize this picture afterwards, right? So let's try to find my mouse because this is the hard part. It's like driving backwards. Okay, let's go back to the presentation. Oops, my fault, sorry. Okay, so now let's jump right into this protocol. This protocol is an addition to Bluetooth, very recent addition to Bluetooth, that allows you to stream data. Because usually in Bluetooth, data is sent asynchronously, right? And when the package doesn't go through, it's retried until it goes through and is acknowledged, and the other side says, yes, I have the capacity to take it. So it's flow control and acknowledgement in the same time. And this isochronous protocol that we are seeing now is different. It is perfect if it's not so important if you lose packages. It's something like the distinction between UDP and TCP that most of you probably know, right? So here it's important that the data actually continues in time, deterministic time, but it's not so important if you drop a packet now and then, right? Bluetooth audio, of course, you don't want your packages to lag behind, so you want them to be sent, and as it's audio, usually you have, in every time interval, you have something to say about your ongoing file that you are sending, transferring, right? So what you can see here is that we have two, this stands for connected isochronous stream, connected isochronous stream. And what you'll see here is two clients, right, receiving data, stream 1, stream 2, receiving data from the central. And you see here above a connected isochronous group. And that's another nice thing that this protocol has, that the standard protocol in Bluetooth does not provide. You can be sure that the peripherals get the data in a deterministic way at the same time. Because, of course, you don't want your right ear and your left ear to lag differently behind, right? So this guarantees that you get the data just with the right timestamp without ever having to provide timestamps. So actually what is happening is that the central has a clock, the master clock, that is accounting for timing of the protocol, and the peripherals, so the earplugs, right? The central is, for example, your mobile phone, right? And the earplugs, they are following the master clock. So no matter if their clocks drift, right? They are always following the master clock. So what you get is really synchronous data streams that can be delivered to different devices, or the other way around as well. You can have synchronous sources on different devices, and those sources are then being collected on a central synchronously. So this is really, I find, a very interesting addition to the protocol, and we also use it not for audio, but also measurements. If you have several measurement streams that are going on at the same time, you never have to care about synchronizing clocks or something. You can let them running for hours, and you always know that they are happening at the same time. If you get values from the different devices, you know that they're within a few microseconds, you can be sure that they have been measured at the same time. And that is very important in certain cases, right? So no problem. As always, you have a downside. As I said, it's possible that you lose packages. I just remember one thing. I was asked to take a screencast, so I have to start the screencast quickly before we go on, because we had technical problems. Let me see whether this is possible quickly. Okay. Get my mouse back. And screencast. No, I'm not sure whether that works. I'll try. Looks good. Okay, should be running. Any questions about this? Was this halfway clear? I mean, it's a very, yeah.
Some weeks ago, I read something about a replacement for the induction loops for hearing aids.
That is quite possible that it goes together because
authentication without pairing.
Without pairing, not sure. I mean, there is a pairing mode in Bluetooth. Oh yeah, you're right. That's possible. There is a broadcasting version of this. Yeah. So this is connected isochronous streams, and there's also a broadcast version that you don't have to identify. So it's like advertising, but it's happening on the normal data channels of Bluetooth, right? Where you have a lot of bandwidth, right? And then it can be broadcast to many devices at the same time. And that's probably what you heard about. No need. But we use the connected channels here because those allow us to have security. Those allow us to have clear information of where I'm getting the data from, right? So if you want to distribute to certain devices right and left earplug because it's your music and you don't want your neighbor to hear the same music, then you use connected channels. More questions about the protocol? We are jumping deeper into it, so it's not necessary to understand everything yet. But so far, any questions? Okay, great. Feel free to interrupt me anytime, right? So now we went in a little deeper, right? So what you see here are the places where you can place data. This is also called a time division protocol, TDMA, multiplexing protocol. So you have specific places where the devices can send or receive data. And that's also a great advantage because you don't get collisions inside your own system. Of course, you can have external interference. But if you're using asynchronous channels, it can happen that you get intersection with your own stuff. So we are now looking at one of these intervals, right? So at one slot where data can be exchanged between the central, right, and the peripheral, your earplugs. So let's look at that. Very simple. The central always starts talking to the peripheral. It can be just, I'm here, but it can also be data, right? And then the peripheral, after a short time, it's possible for them to answer. They have to answer, right? At least they have to say acknowledgement or not. Of course, the package can be lost. That's all accounted for in the protocol. But in principle, that's always the thing, right? The peripheral can just acknowledge what has been sent, or they can send data back. This is all configurable, right? This protocol is much more configurable than what you know from Bluetooth usually. That's also an advantage. So you can configure bandwidth, everything, right? You can say it's only in one direction, unidirectional. You can say it's bidirectional, etc. Many things to configure makes it also very complex, right? But obviously, one thing is very important. You need those clear timestamps like, right? Previously, you had the connection events, and now you have this additional timing which is required for all the devices being synchronized together. Good. Yeah, and then obviously also you have to send your data at some point to the stack. You have to tell the stack, I mean, the application has to send something to the Bluetooth stack. And as it's isochronous, you want your data to be inserted somewhere here, here and here if you want to send to the peripheral. And of course, that should be perfectly aligned, right? So you need to synchronize with the data stream. That's rather easy on the central because, as I said, that's the master clock, so you can just use your system clock on the central. But on the peripheral, you have a problem. You have to synchronize to the master clock, so the stack gives you a way, in principle, to synchronize to the master clock by asking what's the time on the master clock, right? And then again, you have to synchronize your data here, but at any time it can drift, so you have to answer this question first or ask this question first, and then you have to synchronize for every packet. So that's the hard part. Right? Any questions until here?
So, but after this initial pulse, the synchronization is assumed done and perfect, and then I can.
Which initial pulse do you mean? This one?
C to P, yes.
It depends where you are. If you are the central, then you want to insert your data here and be sure that the distance between the point where you enter your data and this point is deterministic. There you can use the local clock because you are the master, right? If you are the peripheral and you want to send data, then you want to insert it somewhere here into the stack, right? And that one is depending on that one, right? So you cannot synchronize to your local clock, but you have to ask the central, or in that case, the controller, what's the time on the central? And then, I mean, you're asking somewhere here probably, right? And then you calculate the point of time here, and then you insert your data, because that's very short. So the clock cannot drift a lot over that time, and there's certain window widening, it's called, window widening, that helps you to set your package at the right time. But you need to synchronize still to send your data here, and you have to do it on the master clock, okay? That's challenging. Whenever you do a time division multiplexing protocol, you have that problem. You need a central clock. Think of PTP, for example. You have a central clock, you need to distribute time, and all the peripheral clocks need to adapt to the central clock.
But the synchronization here is not shown.
No, it's not shown, but we'll see the synchronization error soon in the tracing, right? And that's very hard because, as you know, so now we come to this picture again. You know it already. I teased it in the beginning. The problem if the synchronization is not right, that it can be not right for some packages, not right for all packages. It can be that every 1,000 packages dropped, right? And probably all of you that have ever programmed know that race conditions are really hard to debug, especially if they are probabilistic in some kind, right? And that's where tracing really shines, right? So usually you would say, if it's not so time critical, you'd say, I'm just doing some logging, right? But you cannot do logging in these short intervals. It just doesn't work. We'll see a trace later of a log that's like that. In that resolution, writing a few logs is like that. It's huge. So you can't use that technology here, right? You need something that is faster. There are, of course, hardware traces, but you need a big purse to buy them, right? They are really expensive compared to this technology. And this just works with almost any J-Link that you use, right? It's based on the proprietary technology, RTT. Probably most of you have heard of it if you're using J-Link. That is nice to interchange data without a lot of overhead. So this is really some cheap method.
How? It's just a J-Link.
It's just a J-Link. You can use any J-Link. You just need RTT technology, right? But as I said, you need to license it if you want to use it outside of open source, okay? So let's look a bit, okay, let's go back just to see the similarity, okay? You see central peripheral, peripheral central, that's the first interval, and you have the second interval, same again. And now look at what we are capturing live. You see the same here. This goes up because sending and receiving data is, of course, power intensive, yeah? Intensive, and here is preparation of data for that one. So up here you can see that the sending and receiving of these packages is very fast, so you can barely see it, but you see that the Rx, sorry, I have to go here, maybe I'm out of the camera now, that the Rx thread is being active here, so we are receiving data, and directly behind we are sending data. I can see that in the log. I just covered the log because it would be so small you couldn't read it. So here we are switching on-off radios, that's to be ignored, but here again we send the data. You see this is longer now, right? We send like 250 bytes or something, so this takes more time. We are on a 2 megabit PHY here, 2M PHY, and then you see the acknowledgement coming back from the peripheral. So that's exactly the thing we expect, right? Can you see the similarity? Clear to everyone what we are seeing here on screen now? Great. Okay, so you can really follow single packages now by these two technologies, right? That's the way to debug race conditions in an RF protocol. I usually don't work with Bluetooth, of course, that closely, but you need the same technology on the 802.15.4 side, and that's, of course, daily business then, right? If you have problems with your protocol there.
Is this measurement on the central or on the peripheral?
This measurement has been done on the central. Everything that we see is on the central because the bug is on the central. You could do exactly the same thing on the peripheral, of course, but we are looking at the central because that's where it doesn't work. Okay? Good. Yeah. That's what we want, right? 1 PDU every 10 milliseconds. So this interval is 10 milliseconds with the 2 sending cycles, right? With the 2 subintervals. So what we want to see, you can see here, maybe you cannot read it, but it should say 10 milliseconds up here, right? So what you're seeing here is exactly 10 milliseconds. If I switch to the next screen, I will see exactly the same picture again. Every 10 milliseconds, we expect exactly this picture. We should see data preparation here. That's where the data is inserted, and we should see data sending here. Make sense?
Yeah.
Great. And that should be absolutely deterministic, even if you let it run for hours, right? The clock may drift on the central, of course, but as long as you have the same counter below, it doesn't matter. You should always have exactly the same amount of cycles between the point in time where you start inserting your data and the point in time when they are sent. But that's not what we are going to see, right? What we are going to see is that the central happily runs. It doesn't crash anything, right? It looks good. But if you look at the logs, you cannot read it probably, but in that case, I only got 70 packages, or 69, right? So that's what you're going to see. So something is wrong. It works for the first 69 packages, but then connection not dropped, right? It's still connected. But no more packages arrive. Oops. So debugging this is hard. Do you feel prepared now to understand what we are seeing? Right? So I think you learned a lot about if-the-cron's protocol as well, but we need that background, of course, and maybe it's interesting even, right? Okay, let's see. So what do we see actually? Now this is again a GIF, so I'm going outside the presentation mode again. Ooh, that doesn't look good. Like, you see, that's our sending point. I'm synchronizing on that, and you see how the packages crash into that. That cannot work. And if you count, it's something like 60 cycles that it takes, sending cycles, 60 times 10 milliseconds that it takes for the crash to happen. So that's beautiful. I mean, of course, it took me almost 2 days to get that picture, so you won't get it very quickly because you have to find, I mean, in the beginning, you have a big pile of data and you have no idea where the problem lies. But at one point, you should arrive at a picture like that that clearly tells the story, what's happening. So this is definitely a race condition, right? And you would probably not see it well like that in any other case. So we are trying to reproduce this picture and the other one after the fix. That's what I'm trying to do now. And yeah, let's go on. I'm going back to the presentation mode. But this time, I hope I do it right. I think I need to go to slideshow. And then
Florian, go to the lower right side.
Oh, lower right side.
Yeah, right
Oh, nice.
The minus button.
It's always good to have.
This one, yeah. That's my business.
Ah, it's always good to have professionals here in the auditorium. Really, thank you. Oh, this is, by the way, generated by artificial intelligence because I didn't find a license-free photograph that showed it well. Have you seen it? It's artificial, the picture? No? Good. Okay, so now we are diving deeper, right? So I was looking at the point where the packages actually got lost. So this is the exact point where the problem starts, right? So here we can see that we are still, so I did a customization of the events that you can see here, so I can demonstrate it. This is the hard part, but we won't go too much into that. Really, that's depending on your problem. So I created those additional events that really show what's going on. You can see we are producing a packet here of length 194 bytes, right? We are enqueuing it under a payload number 53, right? That's internals of the protocol. We can see that those 194 bytes are sent over the air. We can see that a new packet is scheduled, right, with 4055. So this is already a bit strange. Why is the new packet scheduled already now? Of course, because we are close to the crash, right? And then you can see it's correctly dequeued afterwards. But now look what is happening here. So we are producing the packet, and before it's even in queue, the TX tries to start. Then, of course, there's nothing in the queue. So we get 0 bytes sent, and then the dequeue happens before we ever had a chance to send this. Can you see the difference of the two? Right? So that's the needle in the haystack that you have to find. Once you see something like that, you have always won, because now you know what's happening. Okay, there's a race condition. This one is a race, right? That also doesn't look well if you look at it from the graphical side. And you can see the same thing on the side channel attack. You see that you get a long package here. That's the 194 bytes. You can see here the catastrophe happening. That's log interfering, right? That's logging now. The log says nothing to the output. It's just being active because I have logging switched off actually, so there's nothing to output. But I just switch the log subsystem on for you to see how that can interfere, right? That's really obvious, right? And then from there on, it's 0 bytes. You can see that that's really much less wide than this one. Can you see that? Okay. It's a little bit like the doctors that look at those gray pictures, right? And you need a lot of experience to see something actually, but I hope I make it transparent to you what is happening here. Okay, and you can see, that's what I meant, yeah? You can see how the logging is interfering here. It takes up all the capacity of the CPU, right? Good. Yo, this is a bit, it's more to read for those that cannot really participate. So I tried to fix this. I didn't succeed in the beginning. So I tried to fix it with timers, but as I already said, the timers will only work on the central, not on the peripheral. But I thought, okay, if I fix it on the central, at least I have got something. And that's what I wanted to present actually here, right? Because it somehow worked. But then I tried it out Saturday night. I thought, oh, I'm just making my slides and then I'm done. And Saturday night, suddenly nothing worked anymore. So I had a white night from Saturday night to Sunday to switch to a completely different approach. And this is the right approach, right? So we are actually using that callback approach. There's a big discussion going on still because I upstreamed my fix, of course. There's a big discussion still going on with the maintainer of the Bluetooth subsystem, whether this is right. So far, it's not clear who has got the better arguments, but I'm still convinced that that's one right. But you can see it online maybe that I'm giving in at some point, and I'm going to create a third version of it. So that's very interesting in open source, right? You never know whether, I mean, you learn a lot, of course. So we'll see that. Very interesting discussion. You can just follow the link that is in the slides and then follow through. Good. I think I don't have to go too deeply into the bug fix. That's not so interesting. We are talking about tracing here. So if you're interested later, I mean, I can show more. Just a quick thing, what the code looked before. Yeah, you can see. We are scheduling work here. I mean, that's only interesting for those who know Zephyr. We are scheduling work here, and that doesn't work, of course. It's plain in the documentation that the work queue does not guarantee deterministic timing, right? And that's what you're seeing. Yeah. It takes longer, actually, than it should, and that's why we crash into the packet. It takes longer. So that doesn't work, right? And in the end, what we have is we have to read it from below above. So we are using a callback after a package has been sent. Once the package has been sent, we get the synchronization data. That works on the central and the peripheral. We send an SDU with a synchronization last timestamp plus one interval, right? That's deterministic then. And then we send it using that timestamp. That's the theory. Okay, if that's the right approach, as I said, I'm not 100% sure yet until the maintainers tell me it is. But that works, I hope. Okay, good. Any questions there? Good. Finally, the demo. Now it gets exciting for me, whether that really works. So let's see, that should be a debugger. Who knows the zone?
Ozone.
Ozone, yeah, sorry. You know it? So it's just a debugger. You probably also use the VS Code debugger, mCortex debugger, whatever. It's just the same thing. The same thing here. You can use it under the friendly license as long as it's for educational use. Otherwise, you have to license it. I'm just using it because it's well integrated with the RTT terminal, a little better than the VS Code. But you can do everything I'm doing here. You could do it in VS Code as well, right? With an open debugger. So that's not really important. I'm just waiting at the main, and now I want to see the tracing. That's live now, okay, and this one, this is system viewer, yeah. This is system viewer, and now we want this to be, that's really hard to, with the mouse here. I cannot even see the button. Is that the play button? Let's try. Is it? No. Okay, it's really hard to see for me. Probably I need glasses, or I really don't see it. Still not. I press F5. That should work. Oh, yeah. No, it doesn't work. That's no. Do I still have something open? Yeah, that's a well-known problem. I had it a lot on Saturday as well. But I should be able to fix that. Let me see that. So we got a zone here. That's fine. Now let's see. Yeah. So there's some defunct processes in the background. I have to kill them, and then hopefully. So a zone is gone. That's good. Let's get it back. And then I hope it works this time. Good. Connect it. And let's see. Okay, that looks better. So here we have a zone again, and now let's see whether I get the system view to work. And there it is, and I press F5. No, it's not here. Where do we have it? Here it is. Press F5. Oh, that looks much better. So in what state are we in now? Here in the zone, we are waiting. We are halted, right? Right at the entry symbol. And we have started system view, but it also tells us target is halted. So it's now waiting for me to start the target to be logging then. This is now the broken version that we see first. And yeah, I try to also log the power data. The problem is that my USB hub is not so fast, and I'm not sure whether it's going to work to do everything at the same time. But we'll try. Doesn't matter. So let's see whether that works. Get it to start. Oh yeah, that looks good. And so you can see we have about 2 milliamps now. This is a lot, but that is simply because the debugger is active. Yeah? But the sending will be so much more power that it doesn't really matter. Because in this case, we don't want to measure power. We just want to see where the packets are, right? We could also use a GPIO approach, of course. That is even programmed into Zephyr, but the timing is more precise if you use this method. So I think I have it for, okay, that's a good way to do it. I can manipulate it on my screen. It was put to 20 seconds. Let's put it to 20 minutes because otherwise we don't have time. So let's see. Oh, I get it back. Yeah, that's much easier than trying to manipulate it with the mouse here. Just move it on my screen. So we let that one run. Now we go back to the debugger, and same thing here. I let it run it. Okay, and now the system view should start logging. And I'm not triggering it correctly yet, so I move back. I configure my trigger to interrupt at the right point. Yep. Come on, RTC 0. No, it was 1. And okay, let's see whether that, yeah, that looks better. Okay, now you're seeing the crash.
Where did you configure it?
Yeah.
Also?
Now the configuration where I trigger is actually done here, up here, right? That's the right button up here. You click on that, and then it tells you what do you want to trigger on. Do you want to trigger on a task, which is actually threads or ISRs, right? Do you want to trigger on interrupts? Or do you want to trigger on a marker? So a marker is simply a thing that you put into the code and that you can trigger on. So if everything else fails, you just put in a marker, and then you're sure that you're triggering at the right point. But I'm using the interrupt approach here because it's fine, it works. So you see that sometimes it blinks a little bit here, and that's simply when the asynchronous control plane is active, right? So still we have the original ACL channel, so the asynchronous channel that is Bluetooth, normal Bluetooth way of working. And from that asynchronous channel, which is actually also, so the connection events are timed. And that's the anchor point from where we measure the ISO, but there can be various ISO intervals inside. So that's why it sometimes blinks, okay? Because that's like if you are on your oscilloscope and some other signal is crossing the signal you're looking at. But I think it's still very clear what's happening here, with the previous knowledge that you have now, of course. Make sense? So let's see what our power measurement is doing. That should, yeah, it's working. So I stop it now. And there's no really good way to trigger on here, because there is a trigger, but you cannot say, oh, don't trigger after 10 milliseconds or something, so it doesn't really work in that case. I will probably not be able to show you the exact point, because it's sometimes 200 packets, sometimes 50 packets. So it would be a lot of searching to find it. But I'll show you the packages as they appear. I just need to increase the... Yeah, that looks good. I should be able to put it to exactly 10 microseconds, move it around. There we are, and move it back. Okay. So this is the picture we are expecting. We are not expecting, sorry. This is the problem here, right? You see that the original picture, which we'll see later, was inserting data. Then comes the... no, sorry, that was acknowledgement, then comes inserting data, and then comes sending data. But you saw that the radio events were in between, and now they are behind, right? I don't know exactly at what point. I mean, at that point, we are still sending data, obviously, right? You see it's large. Now, if I go somewhere in the end, I hope I can show you that. If we go somewhere in the end, yeah, that's good. That should work. Now you can say it's really small here, right? This is CPU being active, okay? So you really have to correlate it with a trace, otherwise you don't know what's going on. And if you put it on 10 milliseconds here, 10 milliseconds on the trace, then it's really easy to correlate it. And of course, you can just compare the package numbers because they have been started at the same time. That was running, so you can see the first packet, the second packet. So it's really easy to correlate it if you know how the protocol works. So you can really see which thread is actually active. Is it really reading, or is it the CPU being active? And this is mostly important because you cannot see in the trace when the sending happens, because that's inside the hardware. All the rest is in the trace anyway. So I just use it to see how long my send event is. Okay, but the really interesting view, of course, is that one. And now we should be able, because it shouldn't show any. Let me stop that. So it can take 1 million events, so it can run for hours, right? Let me see whether I can show you that. That's bad. So I'm going to filter the events so that it only shows my custom events. And then it's much easier to see. Let's move back. I hope we can discover now what we have seen on my. So you can see the package is produced. Then we are queuing it, scheduling, and immediately dequeuing before the transmission takes place, and therefore the transmission is 0. So we can reproduce exactly the problem that I showed on the slide now. This is live capture. Clear to everyone? If I now move to the beginning of the whole thing, then we should see the real thing, how it should look like. Even more. I captured for a long time, so let me see. Oh yeah, that looks good. 90x, where is it? Yeah, that looks good. Let's move it back. So here it's good. You see us, where was it? Produce a packet, 243 bytes, and you can see that it's sent here, 243 bytes. Okay? And this time, as we are initially still, you can see already that's just before the crash. You see? Normally it should be somewhere here, in the good case, and it's just before the crash. But still working, still sending data. Good. So this is actually what I wanted to demo. And now I would go on to fix it, right? I'm showing you the commits that I'm having here. And then...
I have a question.
Yeah.
The tracing, you're just doing it with the onboard J-Link of the DK? Or?
Yeah, the reason is I don't even have to do that. I could definitely use the onboard one. I'm using an extra one. You can see it here. But the reason why I'm doing this is just because the algorithm to put on firmware directly is much faster than if you use the USB DFU upload, because it always uploads the whole package. And I uploaded maybe 60, 70 versions of firmware because before I fixed it. So then it really makes a difference whether you use the fast port or the slow port, right? Mm-hmm. So I'm just using, and also for power measurement, it's nice if you have the power separately.
Yes.
So you can measure it. So actually I'm using, makes sense that you see what I'm doing here. Not just for power, just to power that part here. Yeah. Because if you don't do that, you're getting leakage, backwards leakage through the debugging channel. So you just put power on here, so you have this part powered, the debugging part powered. And that's where I actually deliver the power. So I'm using the source mode in this case, right? You have to be careful to, they said cut it here, and I cut it and I had to reconnect it because in source mode it has to be together. So this is just, you don't need that. Don't cut it, just use source mode. You have to switch that dip below here. Yeah. Otherwise, power will not go through to the chip. And then on that side, I just get the chip powered by this, and then I'm doing the debugging directly through the JTAG.
What is the JTAG adapter? It's so small.
Yeah, this is the normal commercial base Sega J-Link. Yeah, this is it's just a base one, but that one is licensed, right?
Yes. And the license includes the system view?
No, it doesn't. No, you really have to buy that separately. But there's also other ways to do it. I'm just showing it with System Viewer because it's nice because it's so graphical. But Zephyr has like 3 or 4 different kinds of tracers included. And you can also push out your data in a open format, and that you can read with anything, right? But it's for demo purposes. This one is nice because it's colorful and it just works.
And for RTT, only System View works, or can we use?
Yes, because it's a proprietary technology, right? The other ones use other means to log out. Yeah. I've never used it actually because that one works well for me. We'll see how, because so far my work has always been open source stuff, right? So I can use it for that. Mm-hmm. In the future, I'll.
But
Yeah, in the Zephyr documentation for tracing, the only UI they mentioned is trace contrast. Did you ever try that? Because that would be okay.
No. I have a permission to use Tracealyzer, which I'm still, which is still pending to use. Actually, they permitted me that explicitly, but actually, I just use that one all the time.
Yeah, well, interesting because that one would be open source, but I don't know if it has the same features.
Good question. Good question. We should try it out. Yeah, actually, I don't know. Should we fix it?
No.
I'm probably long behind my time, right? I have no idea. I didn't put the clock on, but I'm hoping that you're not too tired. So let me show that. Okay, let's see. So what you had just now, what was this tracing here? I won't go into too deep. I mean, you can ask questions, or even after the talk later on, right? You can come over and I show you everything. So I put in a tracing instrumentation here. You can just read the documentation. It's very easy. It's hard to find the right places where you put in your traces, right? You have to go through the different layers. And then I fixed it simply. I did it in 2 commits, so it's upstreaming. It's possible to upstream it, right? And we debugged right now on that point, and now I'm going to that point, and we are building it again live. And then from there, we are trying to debug again. So let's see the build process. It's the normal build process of, so let me see, that should work now. Great. And now, right, I should be able to just build it. Does it do something? No. Now. So I'm building the new version. Done. Okay. And one thing that is nice about Ozone, every time your binary changes, it's automatically uploaded once it becomes active. So, assuming you have a mouse ready. So let's go back. So here we go. You can see how it's uploading automatically. I hope it works. Yeah, looks good. And that's much faster than what you see if you're using USB, because it's erasing everything, etc. It takes like 10 times more. And you can see it already stopped at the right point. So that's really nice to use. And now let's hope that the system viewer does not fail us. Let's start it again. So I'm just pressing the little green button again. We are not lucky. I have to. So this is really sometimes a little brittle. If the system viewer doesn't start, you just close it, reopen it. Might be also a problem just on Linux. Not sure.
Software.
It's just software, yeah. Okay. Where is it? There it comes. Let's try again. Okay. Like always, it's the presentation problem. Okay. Let's try again. Dead. Now my Ozone has also crashed. It's real life. Okay, let's go in. That looks good. Restart it, reconnect. That looks better. Good. Let's see whether system view now works. Oh, yeah. Okay, we are fine to go. So blank system view. Same situation as before, right? We are waiting at the entry point. I'm starting it off, and let's hope that system viewer now does what it should. And I need to adapt but you can already see it's much calmer. I just need to adapt the trigger again. And then we should see the picture that we expect.